In this problem from JEST 2024, we are given an ideal gas. Its adiabatic index gamma is equal to 3 by 2. It undergoes two processes. The first one is reversible isothermal expansion. In this process, its volume is doubled. The second process is reversible isochoric process. In both the processes, change in entropy is same. We have to find the ratio of final temperature to initial temperature. An infinitesimal change in entropy, ds, is defined as dq reversible divided by T. Now dq is equal to du plus pdv from first law of thermodynamics. The first process is isothermal. In isothermal reversible expansion, we have T equal to constant. This implies du is equal to 0 because u is equal to f by 2 nRT for ideal gas. If T is not going to change, u is not going to change. Therefore, we have du equal to 0 for isothermal process. This implies ds is equal to pdv divided by T. Now for an ideal gas, PV is equal to nRT, which means P is equal to nRT by V. So if we substitute this here, we get ds is equal to nRT by V dV divided by T. T and T gets cancelled. Therefore, we have ds is equal to nR dV upon V. Now if we integrate this, we will get change in entropy for the first process. This will be equal to integral nR dV upon V. Now in this process, volume is changing from V to 2V. The volume is doubling. This is equal to nR ln Vf upon Vi. Vf is 2V and initial volume is V. This is equal to nR ln 2. So this is the change in entropy for the first process. Now let's see what is the change in entropy for second process. In the second process, which is isochoric process, reversible isochoric process, volume is constant. This implies dV is equal to 0, which means pdv is equal to 0. We have ds is equal to dq reversible divided by T. Now from first law of thermodynamics, dq is du plus pdv divided by T. This is equal to, since pdv is 0, we have ds is equal to du by T. Now du is equal to ncv dt. Therefore, when we integrate this, we will get delta S for second process. This is equal to ncv integral dt upon T from Ti to Tf. In the first process, which is isothermal process, the temperature will not change, which means Ti will be equal to Tf will be equal to T for first process, because first process is isothermal, temperature is constant. Now in this process, we have change in entropy is equal to ncv ln Tf upon Ti. Now we are given that the change in entropy for first process and change in entropy in second process both are equal. This implies this is the change in entropy for the first process. nR ln 2 is equal to ncv ln Tf upon Ti. N gets cancelled. Let's find the value of Cv. To find the value of Cv, we are given some information, which is gamma is equal to Cp by Cv is equal to 3 by 2. Cp by Cv is equal to 3 by 2. This implies Cp is equal to 3 by 2 Cv. We also know that Cp minus Cv is equal to n times R. When we divide Cp by n and Cv by n, then this is equal to R. This is called molar heat capacity. This is simply heat capacity. So molar heat capacity is denoted by small letter Cp minus Cv is equal to R. Now Cp is found to be equal to 3 by 2 Cv. 3 by 2 Cv minus Cv is equal to R. This implies 1 by 2 Cv is equal to R, which means Cv is equal to 2R. Cv is equal to 2R is substituted in this equation here. Then we will get R ln 2 is equal to 2R ln TF upon TI. R gets cancelled. This means ln 2 divided by 2 is equal to ln TF upon TI, which gives TF upon TI is equal to ln TF upon TI is equal to 1 by 2 ln 2 can be written as ln 2 raised to 1 by 2. Therefore we have TF by TI is equal to 2 raised to 1 by 2, which is equal to root 2. Therefore the ratio of final temperature to initial temperature is root 2.